and I'm doing this vertical live stream on YouTube, which is actually my second attempt to do a vertical live stream on a little bit more advanced topic. The topic for this live stream is TPM 2.0. We're going to design an open source hardware two-layer printed circuit board with TPM 2.0 for Raspberry Pi, like this Raspberry Pi 5 here. I've already made one board. It has some glitches, hardware glitches, actually a hardware patch that I'm going to show you. So today I'm gonna explain how this thing works. We're gonna do the next iteration, and hopefully later on I'll do a proper regular long video to summarize how this thing works and how to use it. So obviously, the first question is, what is TPM? It stands for Trusted Platform Module. Let me show you my screen. I'm going to be sharing my screen like that. So this is the article in Wikipedia, Trusted Platform Module. It's a secure crypto processor that you attach over typically over SPI or SPI. This is not something new. It has started more than 20 years ago in 2003, but the latest version is TPM 2.0. It is typically used for platform integrity and disk encryption. It also has a hardware random number generator. So Raspberry Pi, on the other hand, is a single board computer with the size of a credit card. I believe that anyone watching my YouTube channel is familiar with Raspberry Pi because I have covered it in numerous videos. So this is Raspberry Pi 5. The Raspberry Pi 5 and actually all Raspberry Pi since 2014, this is more than a decade ago, have 14-pin header on the top. The very first models of Raspberry Pi had 26 pins, and in 2014 Raspberry Pi introduced Raspberry Pi version 1 model B, which had 40-pin header, and since then they have been manufacturing new models and versions with 40-pin header like this one. This is a header that allows you to attach add-on boards known as HATs, which stands for hardware attached on top. There are very strict specifications. What is a HAT actually? It must have a specific size, it must have an EEPROM with a device tree binary overlay. So today we're not going to design a HAT, we are going to design just a simple add-on board for the TPM 2.0 module. So this is the first iteration that I did, this little board here. So this is an open source hardware board that I've designed in KiCad. Unfortunately, as I mentioned already, it had a hardware glitch, which means that I have to do another iteration, another version, and today I'm going to explain you what kind of mistake I did, because the best way to learn is actually from mistakes. So how to use this thing? Well, basically you put it on top of a Raspberry Pi, and you have to put it on the SPI pins over here. Once it's connected, it will be it doesn't work automatically, of course. You need to load device tree binary overlay specific for TPM 2.0, and I'm going to explain you this from the software side. On this micro SD card, I've already flashed Linux distribution. Typically on Raspberry Pi, I know that most people are using the Raspberry Pi OS, but this is not the case on this micro SD card. Actually, I have created a custom Linux distribution using the Yocto Project and OpenEmbedded. I have video series about the Yocto Project and OpenEmbedded on Raspberry Pi, specifically on Raspberry Pi 5. So if you are interested in the software side of things and how to build a custom Linux distribution, I recommend you to have a look at these videos. But this is not the topic for this live stream. The topic here is TPM 2.0, and the purpose of this custom Linux distribution is just to try out what I have created. So for the moment, let's remove the TPM module. Right. I'll switch the camera again. All right, so here it is, and you can see I have hand soldered it, so it's not the best soldering that you can find out there. Let me focus it. Okay, and there's a small wire. Do you see it? This small wire is actually the hardware patch because I forgot to wire one of the power rails, so I had to use my soldering skills, which are not that good actually, but I managed to get it working. So this is the very first prototype, not very successful prototype, but obviously a working prototype. So now let me show you on the back on my computer how I have designed this thing, and then we'll proceed to testing it. All right, so I'm using KiCad. KiCad is free and open source software for designing printed circuit boards. The whole purpose here is, here's KiCad. So the whole purpose here is that, in my opinion, if you are doing open source hardware, it doesn't make any sense to use very expensive proprietary tools to design these boards. And KiCad is a free and open source software. It's a great software. I have been using it for many years. I've started using it thanks to a recommendation by my friends here, a quite famous company in Poli, Bulgaria, where I live, which is called Olimex. So they've made some workshops. Shown that's how I learned how to use KiCad, and I started dealing with it. So here is KiCad. So let me open the project. Here we go. First, the schematics. These are the schematics. I hope you can see them, right? Okay. So this was the initial version 1, right? It's nothing that interesting. It has Optiga TPM SLB9672, right? So this is the chip here, and I have selected a footprint appropriate for this chip. Here we go. And I have wired it according to the data sheet. So if we go, and by the way, today I'm having my cup of tea with a Mauser mug. I'm using and working with Mauser quite a lot. Mauser is probably the largest electronic store. They have very quick delivery, and actually we're going to do a quick unboxing later on in this video. So if you want to buy components, Mauser is there for you. The good thing is that they offer a free delivery for any orders above 50 euros, which means that I can get stock from Mauser. With their warehouse is based in Texas, but they ship really quick with FedEx to Europe, and they deliver it for free if you have enough quantity. So that's how I got my TPM modules for the next prototype that I'll have to do. So switching back to the Mauser website, here we go. I've entered here SLB9672. Here is the one that I'm looking for. It is made by Infineon. You can see the prices over here. So the prices depend on the quantity. The more you buy, the better price you get. Here, Mauser also shares the datasheet, which is the most important thing when you are designing a printed circuit board. All right, so here, somewhere here, there's a typical. All right, here is the chip. It's really small. This is the packaging UQFN. So it's really small. You can see all the pins around here. This table here is quite important because it explains the input-output signals, table 3. Table 4 is something that I didn't pay enough attention initially when I designed the very first board. That's why I had to make this hardware part. So table 4 explains the power supply. There are 3 pins that we have to connect to the available voltage, which in my case is going to be the 3.3 volts coming from Raspberry Pi header. And there are 4 pins that we have to connect, all of them to ground. There is one remark actually over here. So here is, this is pins 8 and 16 can be connected to voltage or ground to be compliant with the TCG specification. All right, so it's good to have them connected if we want to be fully compliant. Here are the typical schematics. It's relatively simple. There are some pull-up resistors, 10K pull-up resistors. The typical schematic in the datasheet adds just one of them to cable select. You're gonna see in my design that I've added also to the interrupt and the reset signals this type of resistors. The other important thing is here the capacitors. So there are 4 capacitors. 3 of them are 100 nanofarads, and they should be placed close to the device VDD/ground pins. Okay. The rest of the data sheet is not that important for the things that I'm going to do right now. So back in KiCad, this is the schematics view, and this is the board. Okay, you can see the board here. Out of this, we created this. So actually, I have to rotate it like this. So this is the very first prototype. So what's wrong? What's wrong in it? Let me know in the comments if you see what's wrong with this first version. I've already told you I made a change, and I'm gonna do a second iteration because I had to do a hardware patch to get this thing working because of the mistake that I made. But after all, it's the best way to learn is from mistakes. So over here you see pin number 14 and it's not connected. However, in the data sheet, if we have a look at the table again, where's the table? We have to connect pins 1, 14 and 22 to VDD, which in our case is 3.3 volts, somewhere here, right? The other things that I have to check to be compliant is pin 8 should be connected also to 3.3 volts and pin 16 to ground. Let me see if I did this actually. Pin 16 is connected to ground, here we go, and pin number 8. Here we go, here is, sorry, this is pin number 8, which is also connected to 3.3 volts. That's all good. If we run the test, there will be no mistakes. This is, so basically KiCad has this feature to run some tests to make sure that your board is properly wired. This is a kind of a sanity check. So before you export the Gerber files and give them to a factory to manufacture for you prototypes or actually a batch of boards, you have to run these tests to make sure that you properly wire the board. So here there are no errors, but actually there are no errors because I made a mistake on the previous step on the schematics. When you're designing a printed circuit board, you go through several steps. The first step is obviously to create the schematics. After that, you have to assign footprints to each component on the schematics, and then you have to export the schematics in the PCB view, the thing that I've just showed you, and to put traces and to create your actual board. So in this case, my actual board is fine according to the tests, but in reality it's not, because I made a mistake on the previous step where the schematics are. So let me switch back to this. I don't want to save the changes. All right, so the schematics, the problem is over here. I have to change them. So I have already done this. I don't want to go into too many details during this live stream. The whole project is available actually in GitHub. So let me show you the project in GitHub. It's an open source project, so the idea is to be shared. Here is the TPM project. So the whole KiCad project is over here, and this is how I'm working. This is what I'm using to work. So now, right now, I'm not using the latest version because I checked out the previous version to show you how it works. Let me pull the latest version. I'm gonna switch to the main branch, and after that I'm gonna type in git pull. Already up to date. Here we go. Revision 1.1, and I have connected pin 14 to 3.3 volts. This means that now I'm fully compliant with the instructions from the datasheet, which says to connect pins 1, 14, and 22 to 3.3 volts, in our case for the Raspberry Pi. So let me show you this git commit. I know that Git is a version control system. So typically it's used for software projects, but it's also great for open source hardware projects because it keeps track of your changes, and you can revert, you can see the history, you can see what other people are doing. And the best thing about KiCad, using KiCad with Git, is that actually this way you can have people from different parts of the world interacting together, just like on a software project. But in this case, we're using Git for version control of a real hardware project. So if I show you this commit, you're going to see that actually the KiCad files are text-based. The KiCad files are text-based, and we can see the changes. They don't make a lot of sense for human readable text, but you can see the changes between the two versions. So I'm using now the latest version from GitHub. Actually, the Git repository in this case is in GitHub. Actually, I'll switch to projects just to make sure that KiCad loaded the newest version. And now here is the change. On the schematics, let me zoom in. On the schematics, I have wired this pin number 14 to 3.3 volts. The other two important pins, VDD1 is also connected to 3.3 volts, and pin number 22 is also connected to 3.3 volts. So here you can see the resistors that are connected to 10K resistors that I told you. They're connected, in my case, I have them for the reset, for the interrupt, for the cable select, for the interrupt, and for the reset. This is according to the data sheet, which have this typical application just for the cable select, but I decided to extend this and to have them also for the interrupt and for the reset. The rest of the pins are for SPI communication. So SPI, let me open it in Wikipedia. This is Serial Peripheral Interface, SPI, and I think people are calling it SPI. In English, I'm not a native speaker, so sorry if that's not a correct pronunciation. So it's a de facto standard for synchronous serial communication used in embedded systems. And on Raspberry Pi pinout, okay. So on the Raspberry Pi pinout over here, we are using these 3 pins for the SPI communication. MOSI, MISO, clock, we're also using ground. The 5th pin is for the power. So our board, the board that I've designed over here, is going to be plugged this way on the Raspberry Pi. That's really important. Okay, so now back to the KiCad schematics. The other important thing is how we have the resistors. It's exactly, I've followed exactly the recommendations from the data sheet. So here you see the data sheet, how it is, and I'm doing the same. All right, so now here we can run electrical rules checker. There are no errors, no warnings. The schematics are fine. Here is the connector. This is basically this thing here over here. Now Yeah, one more thing actually. So in KiCad, when I press the E button, we can see the footprints that are assigned. The most important footprint is obviously the TPM chip, the Optiga SLB9672. There are several versions of these chips, so the last letters don't matter that much in terms of the schematics because they're all pin-to-pin compatible. So actually here I'm using a footprint for XU, although actually I think I used VU for the prototype, but it doesn't matter much because they're pin-to-pin compatible. So now this is the second iteration of the board. Now let's switch to the PCB editor, and you can, if you remember what you've seen before, now you can see the change over here. I added a bias and this trace to connect pin number 14 to 3.3 volts. This way, this should work. And now this here is the header. This is the header that will go to the Raspberry Pi according to the schematics, of course. Everything looks very big when you look at in KiCad because you can zoom in and out, but in reality, the chip is really small, and the board is really small. And over here, it's barely seeable. Let's see, there is a small mounting hole, really small mounting hole, because this is the mounting hole, right? Let me show you it in the 3D viewer. KiCad also has a 3D viewer. Oh, this is the opposite side. So here between the capacitors, there is a mounting hole, really small mounting hole. So basically this is because there is a security breach with the way this TPM will work on the Raspberry Pi. By default, Raspberry Pi does not come with a built-in TPM. That's why we're designing this board. We're going to connect this board to this Pi on the Raspberry Pi 40-pin header. However, this means that anyone can interact, intercept, and make man-in-the-middle attack and listen to the communication going on between our small board here and the Raspberry Pi. This is a security breach. So there are not so many ways how to solve this, and one of the ways is to actually have hardware protection. And this means that with this mounting hole you can put a very tiny screw or some kind of a steel rope to fasten literally fasten, mechanically fasten this module near the board within your case, and this way to prevent man in the middle attack. I see there are some commands. Thank you very much for adding commands. It's fantastic to see anyone watching my videos, and it's even better to see people that are tech-savvy users asking questions. So the first command is that someone likes to hear about this topic. That's great. The second one is, are you using a plugin for Git? No, I'm a Linux user. So what you see here is, let me actually switch. Is a ThinkPad. I'm also a ThinkPad guy, as you know from my other videos. So I have a ThinkPad. This one is with a German keyboard because it was a very good deal. So I'm using it with Ubuntu. So it's Ubuntu 24.04, long-term support. Ubuntu is very simple to use Linux distribution. It's made by a company called Canonical. So I'm using here Ubuntu, which is a long-term support release of Ubuntu. Every 2 years, Ubuntu makes long-term support release. Otherwise, they also make short-term releases every 6 months. But I'm getting old now. Nowadays, I'm using the long-term releases. A few years ago, when I was younger, I had more passion about it, I guess, and I was using every new release every 6 months. I was updating. Nowadays, I'm updating every couple of years. So this one is with Ubuntu 24.04, which means that this version was initially released in April 2024 last year, and after that I keep updating it. I regularly keep updating, of course, the long-term support release of Ubuntu. So I have no plugin for Git. It's just the terminal. Ubuntu nowadays comes with the GNOME desktop environment, which works on Wayland, and this is the terminal application within the GNOME desktop environment on Ubuntu standard. I haven't made any changes. What you see here is a plain Ubuntu, and all the software that you see here, like obviously Git and KiCad and the Chrome browser, they work flawlessly on Linux, specifically on Ubuntu. So if you're not a Linux user yet, I highly encourage you to give it a try. You can buy an old ThinkPad, for example, and try out Ubuntu on it. You're gonna love it. It's so good. So yeah, it's no plugins, just plain Git. Right. So back on the board, here is the board. Once the new version is ready, I have to export the Gerber files. So the Gerber files are basically like, think of it as a PDF that you give, if you have some kind of a poster to print, you make a PDF, you give it to a studio that has a high quality printer and they print it for you. Well, it's a similar situation with printed circuit boards. So you generate Gerber files. These are universal files that you provide to the factory, and the factory makes prototypes for you, or actually real boards. So I'm going to plot the Gerber files and the drill files. The drill files means that where to cut, right? So you have to generate both Gerber and drill files, and once they're generated, in this case in this directory, you can zip them, send them to the factory, and move on forward. I've already done this actually, so in maybe a few days I'm going to receive my prototypes, and we're going to have a longer video about this. There's a nice joke here. So you're saying what you see is what you get. Yes, exactly. And if you want to have a look at this project on your computer, you can do it by checking out the Git repository ANAVI TPM 2.0, which actually it's private. Wow, that's a mistake. This was not on purpose. Well, this is these are, you know, the curse of the demo and the live stream, I guess. Where do you change? Okay, we're gonna change the visibility. Sorry about that, and thank you very much about this command, because actually this made me check it, and all right. Oh, okay, so I have to type in an authentication code. All right. I have to open my, this is gonna be okay. I hope I'm still live, right? Sorry, I had to do this. I'm new to vertical live stream, so I'm not sure if the live stream was going on while I switched the applications. I had to check I had to check my code to switch to this repository to public. Thank you very much for this command again, because it helped me figure out that actually it was private. No, it's public. You can have a look at it. You can download it. You can use it. KiCad works on, you can download KiCad for free. It runs on Windows, Mac OS, and Linux distributions. In this case, I'm using it on Ubuntu, but even if you're not a Linux user, you can still use KiCad and try out this board. So the new version is ready, and recently I received this thing here. I'm gonna open it. Hopefully it contains the TPM module that I need for the new prototype. Oh. Can I do this with my bare hands? I didn't bring scissors with me. Alright, let me see what we got here. It's not just the TPM, of course. This is my order from Mauser that was recently delivered. This is again for Raspberry Pi for attaching a camera for another project, not related to this video, but you're gonna see it in future. These are MEMS microphones. I use them for ANAVI TPM, which is an open source hardware development board. Another project that's not relevant for this video. And finally, here we have from Mouse Electronics, we have the SLB9672 VU20. This is the chip that we need. It's over here. So I bought only two units, which are almost €5. Let's change this to US dollars, as I believe a lot of people are in the US that are watching this live stream are in the US. So it's so it's a bit less than €5 or $5 per one piece, but so it's quite expensive, right? But once you buy like 100 units, it's gonna cut the price almost in two. So this is a good deal, and let's see if I can open it. Okay, here we go. Let me switch, probably you're gonna see it better on the front camera. So just two units, really small. I'm gonna use these 2 units to solder the next version of the PCB that you've just seen in KiCad. But in order to proceed with this, I also need to get my new PCB prototype ready. So once it's ready, hopefully at the beginning in June, I'll get my hands on it, and as soon as I have spare time, I'm going to record it and make a longer proper video to explain how everything works. This live stream is just to, me rambling and showing you some details for people that might be interested in designing printed circuit boards. So this is a 2-layer printed circuit board. If we switch back to KiCad, here, you see this is so now this is the front layer with red, and with blue is the back layer. So there are two layers, front and back. Okay, so now the board has been designed. I exported the Gerber files. I've uploaded. I've already ordered a new prototype. Here I have the new TPMs. They're so small. I just have to make sure that I'm not going to lose them by the time when the board arrives. So we're ready for the next prototype, for the next introduction. But of course, we have the very first prototype with the hardware patch that you see, the wire over there, ready. So let's plug it. In order to plug it, we need to have a look at the pinout of Raspberry Pi. So here is the Raspberry Pi 5, and so this is the very first pin. The 5-volt rail is over here, and we have to count, right? So we're gonna plug our board to these pins from 17 to 25 on the bottom row, and from 18 to 26 on the top row. So we have 1, 2, 3, 4, 5, 6, 7, 8. And on the 9th pin, we have to plug our board. So from that point, we got like here, there's some, a little bit of counting from over here, right? It should go like this. The direction is very important. So my idea is to have this TPM in 2 options. One, obviously like that, but it's going to be in conflict with the fan, specifically on Raspberry Pi 5. And the other option will be vertical, so it's going to be going up like this. Just a different connector with 90 degree angle. So now we have it connected. The second thing that I'm going to do is to connect the Raspberry Pi, the big probe, for serial communication. If you're not familiar with this, have a look at my longer video when I explain in details how it works. It's a really great tool. I'm going to use it for serial communication. All right, I'm connected it like this, and I'm going to connect it to my laptop. All right, here we go. Here we go, right? And now let's connect the Raspberry. Actually, one more thing. On the Ubuntu, I'm gonna open a new tab, and I'm gonna type sudo screen dev.ui. This is the device of the debug probe, right? So I'm going to get the serial communication coming from this Raspberry Pi 5 through the Raspberry Pi debug probe, output it on the display on the monitor of the laptop. So it's very important to set up a baud rate. So here what we see in this command, sudo, I'm executing this as a super user. This is something typical for Ubuntu users. Screen is the terminal application for serial communication. This is the device for the Raspberry Pi Pico, and the baud rate. I'm pressing enter. Nothing happens, just dark screen, but that's totally fine because now we're gonna turn on the Raspberry Pi by just plugging a USB-C power supply. I'm using the official Raspberry Pi power supply, and here we go. It starts to boot. So as I told you, this is a custom Linux distribution that I built with the Yocto Project and OpenEmbedded. I have a video series about Yocto with Raspberry Pi 5. It boots with a custom Linux distribution which I created. It's a headless, so there is no, even if I connect something on the HDMI, I won't get a fancy user interface. It's just headless, text-based command line interface available for this distribution. I've switched to using U-boot, which is an open source bootloader. Again, I have a separate video to explain how to use U-boot on Raspberry Pi with the Yocto Project and OpenEmbedded, and I also set it up with systemd. So I'm going to log in. The user is let me just place somewhere a Raspberry Pi. Can you say that? You can barely see it, I guess. So let me log in. Root without a password. Okay, root without a password. And now so actually I'm typing in on this laptop, but everything that we do is happening on this Raspberry Pi. Root without a password. I've logged in as root. Now the message shows all the messages while the kernel loads. It's a huge pile of messages. Obviously we can't easily go through them, but what we can do is to type in like this pipe, this symbol, grab this command to search for text within other text. So we're going to search for TPM in the output of the message with this command. And here we go, just 4 lines, but this is enough. This says that the device has been found. A TPM error occurred attempting to self-test. That's strange. And starting the TPM manually. So now let's do. I've installed TPM Tools. TPM Tools is an open source software for using TPM on Linux. Here we go. There is a documentation to explain how it works, how to install it, and so on. But I've already installed it through the Yocto Project and OpenEmbedded on the Raspberry Pi. So what we're gonna do here, TPM2. There are a lot of commands, more than 100 commands available for TPM on Linux. So just quick look at them. All right. So TPM, there is a self-test. Here we go, self-test. Let me output the help. So here is the usage. You can type in F for full test. I think also we can type V for verbose. Okay. So I run the test, and now there is another command to check the test results. Get test results. So success. All right, that's successful. Let me know in the comments below if you, for those of you who are watching the live stream, if you want to run another test. There is also a random generator. What was the name of the random generator? Just a second. Get random, yeah. So get random, but we can output it in a file, or okay, we can output it as a hash. That's good. Hex, sorry, not hash. And we can say arguments, options, the number of bytes, I think, like 8. Okay, that's pretty cool. So what gets here is that one of the features of the TPM, apart from the security and cryptography features that we typically use it for, is that you can generate random numbers. This is an external hardware device that allows you to generate random numbers, and with this command that you've just seen, we're generating random numbers. Let me explain once again what's going on here. Sorry if I'm repeating too much myself, but I've turned on the Raspberry Pi with a custom Yocto Linux distribution that includes the TPM 2 tools, which is an open source software. I'm using the Raspberry Pi debug Pro, which is connected to my laptop, and I'm using on my laptop, I'm running Ubuntu 24.04. I've opened a terminal. This is the GNOME desktop environment. This is a terminal running in this GNOME desktop environment, just the standard terminal application, no fancy plugins, nothing. This is how Ubuntu works. And actually, Ubuntu is pretty cool. So it looks pretty well. If you haven't tried out Ubuntu in a while, give it a try because it looks pretty good. So I have Ubuntu running on my ThinkPad. I have this custom Linux distribution running on the Raspberry Pi 5. I've attached the TPM, you've seen that. I have the the Raspberry Pi debug probe, and I'm interacting over serial with the Raspberry Pi thanks to the Raspberry Pi debug probe, because I typed in sudo space screen, which is the terminal, the command line application that I'm using. I've entered the device of the Raspberry Pi debug probe and the baud rate, which is supported by Raspberry Pi. That's how I entered here in this terminal, and everything that I type in here happens on this Raspberry Pi 5. So I've already tested to make sure that the TPM audio is detected by the kernel running on the Raspberry Pi 5, and here is again, it's connected over SPI. I ran some tests like self-text, and after that get results. The test is successful. And now something more practical, that's more interesting, that I've just did. I'll repeat it once again. I'm gonna generate some random numbers in hex. Let's say a huge number. Okay, TPM get random is bounded by max hash size, which is 48. Okay, the maximum size is 48. Here we go. I've generated this huge random number in hexadecimal format. Here we go, and it outputted. This means that the TPM works. The board is fine with this little hack that I did. You see this tiny wire. I'm not sure if the YouTube quality of the video is good enough to see it, but you see this wire. This is the hardware patch that I've applied, because the very first version of the open source hardware 2-layer PCB that I created in KiCad had a design flaw. I have to admit I made a mistake. It was purely my mistake. Sorry about that. We're gonna have another revision of it really soon, and we're gonna cover it in the next video. So everything that I've showed you in this live stream is available in GitHub. This is the project. Later on, once we're ready with the live stream, I'm gonna update the description of the live stream and put a link to this repository. So it's an entirely open source project. I designed it with KiCad, which is free and open source software for designing printed circuit boards. It works on Microsoft Windows, Mac, and of course Linux. I've demonstrated you how to use it on Ubuntu. you can easily install it on any of these operating systems. So no matter what kind of operating system you're using, you can get involved into this project. The tools that we use, TPM tools, are also open source, also available at GitHub. So all these projects that you see here are all open source, and specifically the boards that I've designed, the open source hardware board is also available as the whole KiCad project for it is available in GitHub. And if you don't like GitHub, you can just clone it from GitHub and then put it in your own repository. That's totally fine, because the license that I selected allows you to do this. It's Creative Commons Attribution Share Alike, so pretty much you're free to do almost anything as long as it's open source. You're free to share and to modify it. You can even make designs based on this and sell them, but you must give an appropriate credit. That's all of it. It's quite permissive license. Later on, once I have the next iteration of the board, I'll submit this board to for certification at the Open Source Hardware Association. So thank you very much for watching this live stream. I hope it was interesting. Wow, Argi says that he's watching this live stream at 2:30 a.m. Wow. Wow, it's thank you very much for watching the live stream at that early morning or late night. It's I'm always having this problem to determine if 2 a.m. is late night or early morning. I'm not a guy that likes to wake up early in the morning, so I prefer to work late at night. So I enjoy seeing other people that are having more focused work at the late night, but the 2 a.m. yeah, it's right. And thank you very much for your positive comments. I hope you like them. I'll keep you updated with this. Actually, this format for the vertical live streams is super easy, because I have this very easy setup with my Android smartphone, and I can easily record and share. I hope you can see my my laptop, because I'm not doing proper screen sharing, for which I'm sorry, but I hope that you can still see it pretty decent what's going on my laptop. And the good thing, of course, is that everything is available out there in GitHub and in these Git repositories, so you can easily get involved and get on board. Thank you very much for watching. If you like this topic, please stay tuned for the next videos. Hopefully in June I'll show you the next interaction, and hopefully this time there will be no hardware glitches, so we'll do a proper demo without these crazy wires going from the board, these hardware patches. But this is part of life. In software, it's easy to fix a bug. In hardware, you have these small patches. And actually, I'm really proud that I was able to do this patch over here. I know it looks ridiculous, but it works this way, and I was able to get the board working. Okay, so thank you very much again for watching. See you soon again. That's all from me, and take care. Bye bye.